Hi, everybody. I hope you're doing well and ready to talk about some math. In today's section, section 1.5, we're going to really get into our first calculus topic. So the first chapter A and the first 4 sections of chapter 1 have been review. We've talked a lot about algebra rules, algebra review in chapter A, and then in chapter 1 we talked a lot about functions and a little bit about their graphs, and particularly linear equations and functions and slope. So one of the major things in calculus is to extend the notion of slope to things that aren't linear, which is a really cool thing. We'll get there when we get there, but for now we're going to kind of talk about the kind of underpinnings of the big idea in this class, which is the derivative. And I can't really tell you much right now. We just kind of have to look at limits, kind of like just for what they are at the moment. But when we get into talking about derivatives in chapter 2, hopefully a lot of things will start coming together with regarding limits and the difference quotient and everything like that. So limits arise in real life, like the motivation behind why people started talking about limits. There were mainly 2 questions that drove the study and the kind of the, invention or discovery of calculus, particularly differential calculus, which is calculus 1. There's another kind of calculus, integral calculus, which would be typically studied in calculus 2. So differential calculus, there's 2 questions that drove this field of study. One of them was finding the tangent to a curve at a point. So you might remember in geometry, finding a tangent line to a circle. You have a circle, there are things like chords and secants and stuff. So a tangent line is the one that just touches the circle at one point. Come on, iPad. It's a little too early for this. Touches the circle at one point. Have a tangent line to a circle here. I don't know, this might not seem that interesting to you. We're not going to talk about tangent lines to circles necessarily, but any graph in particular, so say you have the function that looks like this when you graph it, and we want to find the tangent line, the line that goes through this curve at a single point, but has just the right slope. And that's a really difficult thing because slope, in order to find it, you need 2 points. So finding the slope through of a line that goes through only know 1 point on the line, it's not as straightforward as it might sound. The second thing that drove the development of calculus is finding the velocity of an object at a single instant in time. Now, velocity is found by looking at the change in distance. You might remember, I'll talk about this too, over the change in time. It's how far how your distance changes, how far you make it over a certain time period. And so if you take a snapshot in time at just one instant, there's no change in distance and there's no change in time. But at any given instant in time, like we're always moving, right? So there is a velocity or a speed at a particular single instant in time. So these are questions that we're going to answer a little bit later. We're going to, in this section, just develop the mathematical skills and the tool of a limit. We're going to find limits several different ways. We'll talk about all of them, but for now we can think of them as numerically, graphically, and algebraically, with a 4th way that is a little more straightforward. Okay, so you might, when you hear limit, you might think of something like speed limit or, safety limit, some kind of maximum that you shouldn't go past. However, in math class, you don't want to think of limit as being in that way. For some reason, we just chose to use this word. I think you might want to think of limit in math class as like limiting towards or approaching, I think is a really good word to kind of associate with a mathematical limit in this class. So a mathematical limit Again, we want to associate just the word approaching, and you'll see why when we get into it. But a mathematical limit is a tool that we use to describe the behavior, super fancy math word, it actually is, of a function's outputs. Okay, so outputs, these are like the y values, right? Or the f of x values, the outputs, as the input values, so the x values, become closer and closer and closer and closer and closer and closer, or like limit towards or approach some particular number. So we're going to be letting our x values or our input values approach some numerical value. And then we're going to want to look and see, as that's happening, what are the y values doing? Are they approaching something? And if so, that will be the limit. Okay, so there's some notation that we need to get familiar with limits, and it is as follows. So when we want to describe a limit, we write LIM, obvious y, right, for limit. And then underneath the LIM, this is where we indicate what x is approaching. So we write x, or whatever the input is, and then an arrow to indicate that x is heading towards something. And then this is where we put the numerical value that x is going towards, but I'm going to use a letter here. I'm just going to use C, because it could be any number. Then next to this whole thing, limit as x approaches c, we write the formula for the function. I don't know what that's going to be, so we're just going to write f of x. And then if this has an answer, we say that this equals L. And the L will also be a number. Right? This will be what the y values are doing, or the output values are doing, as x approaches c, or whatever number that we have there. So the way, actually, let's just indicate that here. So the c and the L, these are numbers when we actually have a function and stuff like that. We want to get a number out, or possibly infinity or negative infinity. Okay, so just to have a little way of reminding us of like how we say this out loud, what we would say is, there are a few different ways you could say the limit of f of x as x approaches c is L. That's how you could read that. Or you could say, another way of phrasing that was, you could say as x approaches c, f of x, or the y values, approach L. So there's this notion of coordination between the x and the y values. Okay, so this is how we're going to notate limits. There are going to be essentially 4 different ways that we will determine the value of a limit for a particular function. We're going to go through all of them. The first way is called direct substitution. This is pretty much exactly as it sounds. We are just going to directly substitute in the x value. We're going to use this a lot, so I'm going to abbreviate this as ds, because we're going to want to indicate this in our work, that this is what we're using here. Like I said, this is just plugging in the x value. This works sometimes. By work, I mean you get a number out, but sometimes we can't plug in the number that we're finding the limit at. Sometimes the function's undefined at the x value that we're finding the limit towards. And we'll see examples with that. That's not going to affect our answer, because with limits, we just let the input values become closer and closer and closer to some number, but you never actually get there. Okay, so this is the simplest way. Doesn't always work. The second way would be a numerical approach, or determining the limit numerically. This consists of really just, plugging and chugging in your calculator, just plugging in some numbers that are really close to the x value that we're approaching, and then making a chart and seeing are the y values approaching something. So I would say, just to summarize what we're going to do here, make a number chart or a table. Okay, the third way you could determine a limit is graphically. So given a graph, you can read off what the limit is by looking at what the y values are doing as x approaches a certain number or point on the graph. And then lastly, and most importantly, is algebraically. So I'm going to put a little star here next to the algebraically because it's the best way to find a limit. Numerical methods and graphical methods can be a little deceiving, so we do want to focus on the algebraic approach for determining limits. But for now, let's start off simple, and let's go through an example where we can use the first three methods and see how they all kind of give us the same answer or the same value for our limit. Okay, so example number 1, we're just going to look at this simple function, f of x equals x plus 2. And we're going to compute the limit as x approaches 2 of x plus 2. Okay, so when you're finding the limit of something, you don't have to use multiple methods to find the answer. Just for the sake of learning and getting used to what each of these methods consist of, let's try the first 3 ways in calculating this. The algebraic method doesn't really apply here. We'll see that in the next example. Okay, so let's try the first 3 methods. Okay, so with direct substitution, remember we're abbreviating that ds. This would just say, okay, what we're going to do if we're finding the limit as x approaches 2 of the function x plus 2, and I just put parentheses around here, you don't really have to. If we're going to directly substitute in, we're going to put an equal sign, and then above that, to indicate that what we're doing across this equals is directly substituting, and we're going to put a ds. So we're just going to plug in the 2 here. We're going to let x equal 2. All right, so we're going to put a 2 in for x, and so we get 4 as our limit. Now I know that with a limit, x is only approaching 2. It's just getting closer and closer to 2. But if nothing weird is happening in your graph, like if there's no hole or asymptote or anything that's undefined at the point, then it's going to be the same value. The limit will be the same value as what you get when you plug in the actual x value. So when this works, it's really nice. You just have the limit here. But for sake of just kind of seeing how they all, connect together, let's try the next method. Numerically. Okay, so this will consist of making a chart and seeing as you plug in x values that are closer and closer to 2, what's happening to the function values or the output values. So we want to set up, I like to make it horizontally. We're going to put x up top and then f of x in the bottom. Then, because we can approach 2 from 2 directions on the number line, like we can go with numbers bigger than 2 or less than 2, we're going to put the number 2 in the middle, so right about here. Now we don't really, when we're finding the limit numerically, we can just ignore this because we're just, again, looking at what happens as we approach 2. We're going to look and see, are the y values down here? Are they heading towards something 2 as we get closer and closer to 2? So we're going to be looking for some kind of pattern. So you want to think of this as like a number line. So here's 2. And then the numbers that are, to the left of 2 here, all along here, these are numbers that are going to be less than 2. So maybe like 0 is here, like 1 is here. And so I want to get a number that's pretty close to 2 over here, but a little bit less than it. You might say, well, 1 is good, but we want to get closer. 1.5 might be good, but we want to get a little closer. 1.9 is like a good place to at least start. So I would always kind of start about a tenth away. So we'll put 1.9 over here because we want to get closer than 1.9. So, but for now, let's just plug in 1.9 into f of x. So we're going to take 1.9, put it into here for x, right? This would be f of 1.9. So we're just going to add 2 to 1.9, right? And that'll give us 3.9. Okay, we can get closer to 2 than 1.9, right? Maybe 1.99 would be a closer choice. So once we plug that in for x, again, just into here, into our function, f of 1.99, we're just going to add 2, and that gives us 3.99. And we say, okay, these are getting closer to 4, and that makes sense based on what we found in the previous method. However, 2 things don't establish a pattern. We want to kind of always go for 3. So I would say we can get a little bit closer with 1.999. And of course, if we plug that into the function and add 2, we'll get 3.999. So we only did this from one direction. We approached, x is approaching 2, getting closer and closer and closer. And we could keep on going with this, but the idea isn't to do it forever, right? It's just to kind of see what's going on with the y values here, right? So let's just kind of point out what's happening. As x is approaching 2, right? X is heading towards 2. The y values here, I think we can all agree that these numbers are getting closer and closer to 4. So y is approaching 4. We can check from the other side too, though. So let's pick some numbers that are bigger than 2, so on this side of 2, on the number line, but we want to get closer and closer to 2 this way. So, if maybe 3 is over here, then we can get closer enough to 2 by maybe starting with 2.1, right? That's a little bit bigger than 2, but not too far away. So let's do 2.1. I'm going to put it on this end because we're going to want to get closer than 2.1 ultimately. Okay, so we plug in this again into f of x here. So we're plugging 2.1 in for x. We're just going to add 2, and so that gives us 4.1. Okay, a number closer to 2. Now pause this or just try to write down what the next number might be. Sometimes people think it's 2.11 or 2.19 or like something, but those are actually all bigger than 2.1. So we just kind of want to add a 0 in between. So like 2.01 would be closer to 2 than 2.1 is. And of course, when we plug that into the original function, we'll get 4.01. And a number yet even closer to 2 than 2.01 might be 2.001. And of course, if we plug that into f of x, we'll get 4.001. I'm just going to erase my number line here. Right now, again, from this side, as x is approaching 2, but just from the other side of 2, we still have the same thing going on, right? Y is approaching 4. Right, as we look from left to right, as we're pinching in on 2 in the x direction, the y values are pinching in on 4. And so this is how you would determine, like numerically, or how you would show. This suggests, with this method, that the limit as x approaches 2 of x plus 2 is equal to 4, yet again. All right, this method is sort of tedious. You don't really want to go for it at first. In general, there are some cases where this is the way to go. We'll talk about all of that a little bit later. But for now, let's just see what graphically looks like. Okay, so graphically, let's just write here what we're trying to find, right? We're trying to find the limit just because I can't see it anymore here, the limit as x approaches 2 of x plus 2, right? That's our goal. So the function here, x plus 2, we should all know that this is the equation of a line with y-intercept of positive 2 and a slope, right? The number in front of the x is 1, so a slope of 1. So if we were to just sketch a graph of this, okay, label our axes. We've got x-axis horizontal, y-axis vertical. I know I'm only drawing this quadrant because we're kind of only focusing as x approaches 2. So that's kind of where I want my graph to be centered. So I'll just do 1, 2, 3. I know the limit should be 4. So on the y-axis, I know I need to go up to kind of like around there. I'll go up a little bit more. So we'll just say up to 5. Okay, and if we're graphing y equals x plus 2, right here's our y-intercept, right here at 2. The slope is 1, so we'll go over 1 and then up 1, over 1 and then up 1, over 1, then up 1. Now my scales aren't uniform here, like this is scrunched on the y, this is expanded on the x. So it'll look a little less, like the slope is a little smaller, but that's okay. All right, so here, just kind of connect these together. And here's the graph of x plus 2. Right, so what we are looking for, right, is on the x-axis, we are going to want to approach 2. Right, so we're heading towards an x value of 2. All right, so we're going to like kind of march along the graph. Okay, so if we're gonna approach 2 from this side with numbers that are less than 2, we're gonna kind of be like, all right, I'm gonna go along the function here, and I'm gonna see like, what are the y values doing? They're getting a little bit bigger and bigger and bigger as we approach 2, as we approach this point right here. And of course, the y values, right, they're heading towards 4. And we saw that in the chart as well with the numerical method, right? So this is what's happening. This should be the limit of 4. From the other side, you can see that as we go along, so we're approaching 2 from this direction, as we just kind of march along the function here and hone in on x equaling 2, or getting closer and closer to 2, we're kind of just focusing in on this point here. And again, the y value there that we're approaching is 4. And so here's how that would look graphically. Okay, now if you're doing these in several different methods, right, you should get the same answer for every way that you are trying to find the limit. So you can use different methods to kind of just check to see if your answer is correct. But yeah, this is a fairly simple example. So let's look at our second case, our second example here. We'll still kind of use several different methods just to, for learning purposes again, and to see that they all match up. And then after that, we'll get into some specific methods for calculating limits of all different kinds. Okay, so for example number 2, let's find the limit as x approaches 2 again. Oh, a little typo here. That's not what I meant. But now our function is going to be x squared minus 4 over x minus 2. Okay, so f of x now is x squared minus 4 over x minus 2. I want to know what's happening as x approaches 2. So again, let's try several methods. Okay, and again, this isn't necessary in general, but I think it's good to have one example that we go in, 2 examples that we go into depth with, so we can see how everything is kind of, connected and getting to the same idea. So direct substitution. Okay, so if we are going to use direct substitution, what we will say is, all right, if I'm finding this limit, Over the equal sign, we're going to write ds to show that we're plugging in the 2 in for x, right? This 2 is going into x here and to here. So we'll have 2 squared minus 4 over 2 minus 2. Okay, that's 4 minus 4 over 2 minus 2. And so that's 0 over 0. And so this is, remember, we've got, see here, no. 0 on the bottom is not okay. It's undefined, right? So 0 over 0 included. 0 up top is okay. This will just equal 0. But if you have a 0 in the bottom, that's a problem, right? So here, direct substitution is giving us an undefined answer, meaning that 2 is not in the domain of the function. Okay, there's like a hole in the graph, or maybe like an asymptote of some kind. We'll get into that a little more, but when you have 0 over 0, this essentially means that we do have a hole in the graph 90% of the time. So let's note that. So there's a hole in the graph of f of x at x equals 2. That's what this means if we try direct substitution and get 0 over 0 out. Now, if you do graph this in your calculator or on Desmos or any of the other graphing calculators that I link on Blackboard, there's like a section for a bunch of different really good calculators that you can use online. A lot of them will not actually show you this hole because it's so small that you just, like, we emphasize it when we draw a graph, but on a calculator it's so tiny that you just won't see it. So we really need to be smarter than the calculator and be aware of, domain for functions and what things we can plug in and what things we can't. And so 0 over 0 is a good indicator that there's a hole in the graph. Like I said, we'll talk about that a little more in depth a little bit later. So this method's not helpful, but all hope is not lost. We can still find the limit. Let's try our second method here, and that's numerical. Okay, so our chart setup is going to be pretty much the same because we're approaching 2. Again, we were approaching 2 in the other problem. But just for sake of practice, why don't you take a minute to either pause this or set up your chart ahead of me with numbers approaching 2 from both directions. So again, we're going to put 2 in the center. And we need to come up with 3 numbers on either side that are pretty close to 2. And those will be 1.9, 1.99, and 1.999. Then we'll have 2.1, 2.01, and 2.001. So now here, we actually don't have a function value for 2, right? There's no point there on the graph. But that's okay, right? Because with the limit, we're just going to want to see, what are these numbers doing? What's everything around 2 doing, right? Even though we can't plug 2 in, what's going on around 2? So grab your calculator and just make sure that you're comfortable plugging in numbers like this into a function like this. Okay, so just double check what I'm doing is right and that you're comfortable doing that. One thing that might have been an issue if you aren't getting the right answers is you got to make sure that your numerator and your denominator are in parentheses. Otherwise, you'll get something that's quite off. So when you plug a 1.99 into the function f of x, you're going to get 3.9. Right? When you plug a 1.99 into the function f of x, you're going to get 3.99. And when you plug a 1.999 into f of x, you may have guessed that you're going to get 3.999. This looks really similar to the other table. It's almost identical. It is identical, actually. And so from this side, at least, we have x approaching 2. And again, I think we'd all agree that as x approaches 2, the y values are getting closer and closer or approaching 4. Let's check out what's going on the other side. Okay, so when you plug in a 2.1, you're going to get 4.1. Again, check that you can do this in your calculator. When you plug in 2.01, you're going to get 4.01. And when you plug in 2.001, you will get 4.001. And so again, from this direction, as x is approaching 2, we've got our y values also pinching in or approaching 4. And so what this would suggest to us is that the limit as x approaches 2 of this function now, x squared minus 4 over x minus 2, is equal to 4. Okay, even though f of 2, okay, what we would get if we plugged in 2 is undefined. Okay, so there's a hole at the graph, hole in the graph at x equals 2, but everything around it is heading towards the y value of 4. It's just that when you get to exactly 2, there is a hole, right? You can't plug in 2. But around it, the y values are still honing in on that point, y value of 4 when x is approaching 2. So here's what that looks like graphically. And again, if you go ahead and graph this in your graphing calculator or on any of the websites like Desmos, GeoGebra, or Wolfram Alpha, or like I think even Google can graph things for you. But on quizzes and exams, you shouldn't be using these online calculators. So make sure that you are comfortable using your actual real life calculator to graph these. So here's what will happen when you graph that complicated looking function. It just looks like a line. Super surprising to me anyway. In fact, it looks just like the line from the previous example. It's got a y-intercept of 2, and it's got a slope of 1, except at 2, there's a hole. Now, where is the hole? Where the y values are approaching, just as we saw numerically, they're heading towards 4. So as x approaches 2, and on your graph, you can see that this is a line, as we approach 2, the y values are heading towards 4 here. There's just going to be a hole in the graph. Okay, and then the same thing is going to happen as we approach 2 from the other side. They're bigger than 4, but they're heading towards 4, right? We had 4.1, 4.01, 4.001, and then over here we had 3.9, 3.99, 3.999. So there's a hole at x equals 2 with a y value of 4. Right, and then we just have a slope of 1 going up. So here is the graph of f of x equals x squared minus 4 over x minus 2. And again, you can see, right, as x is approaching 2, right, this is where we're honing in on, right, we just kind of go from both directions, see what are the y values heading towards, and they're going towards the same place. And even though there's a hole there, right, the y values are approaching 4. Okay, so this is how graphically we would see that this limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to 4. Again, even though there's a hole in the graph, the limit doesn't see this hole. Right, because you don't actually have x equaling 2. We're just letting x approach 2, right? Limit means approaching. Okay, so this is really cool because before this, we've kind of, in your previous classes, in pre-calculus or like even algebra, you just kind of have this static view of like, okay, I'm going to plug in an x value and then I'm going to get a point out. Okay, then I'm going to keep doing that for different points. And if you can't plug in 2 into a function, it's hard to know what's going on there, for example, here. But with limits, we have this kind of dynamic notion of like, well, we can't just plug in a number, like we can kind of see what's happening around it and then kind of fill in the gaps. Not literally, because we still have a hole there. Okay, so in this example, we can actually use an algebraic approach as well. So numerical methods and graphical methods and everything, those are nice. But algebraically, when we have a hole in the graph, we can use algebra to remove the hole. I don't really like this because removing a hole, I don't know. I feel like it makes more sense to say that we're filling it in. Excuse me. But yeah, so let's see how that looks. And we'll talk about this method in depth for various kinds of functions in a later video. So if we just kind of look at the function f of x for a moment, and maybe you have seen this already or noticed this. Okay, we can actually factor that numerator. It is a beautiful difference of 2 squares, my favorite thing to factor. We will just get x plus 2 times x minus 2. And here we can kind of see the culprit that's giving us a 0 over 0, right? If we just kind of go, well, we just remove those or cancel them or divide them, what we're left with here is x plus 2. That's really interesting, right? That's just the example 1 that we were looking at. And the graph of these are this function here and this function here, right? They're identical except for the fact that there's a hole at x equals 2. Okay, so that's the relationship between this kind of idea. Like if you have a function like this and you cancel out the hole, the graph of the original is going to look just like the graph of what you get after you cancel the hole, except it will, of course, still have the hole there. Okay, so this is why algebraically the graph ends up being how it is, because for every other x value except 2, you're going to get a number here that will just cancel out and you just end up with x plus 2. But it's really important to kind of note here that if we do this, we're actually getting a different function. So I'm going to call this like g of x, this one here. And this one here will be f of x. They are not equivalent functions, right? I mean, their graphs are different. Okay, so it's just important to kind of keep that in mind, that f of x and g of x, and we'll just kind of maybe make this a note, more of like a conceptual understanding of what we're doing here. F of x and g of x are not equivalent. They're not the same functions for several different reasons, right? First of all, f of x has a hole at x equals 2. And g of x does not. Right, that's the graphical reason. F of x's domain doesn't include 2, but g of x's domain does, right? So they're the same everywhere, except that x equals 2. So let's say, well, let's say here, they are equal, they're the same everywhere. They're the same everywhere else though. So the reason why this is important, or what I'm trying to get at here, is that what this will imply then is that their limits as x approaches 2 will be the same. Okay, so therefore, because the limit as x approaches 2 considers only x values that are approaching 2, we can say that the limit as x approaches 2 of f of x is equal to the limit as x approaches 2 of g of x, because x never equals 2. Okay, so what we can do, and we'll get into this, is we can then, we'll have the limit of this equals the limit of this, and then what we can do is just directly substitute in the x value that we are trying to find the limit at when we kind of remove the whole. So it's a way of still easily finding a limit algebraically. This is kind of the why. So like I said, we'll get into the various methods of calculating limits algebraically. It's kind of the toughest way of doing it, but I think that we're pretty well prepared. But before we do that, we have a concept of one-sided limits that we'll get to in the next video. So I'll see you soon. And yeah, bye.